All right, in this worked example, we'll be looking at paper 22, question 2 from the February-March administration in 2019, ACE Physics 9702. All right, define displacement. So in this class, we want to remind ourselves whether these quantities are vector or scalar. So displacement is a vector quantity defined as, all right, I think Lance got it there, defined as change in position in a given direction or in a certain direction. That kind of really gets back to the idea that it's a vector, right? So direction matters. Defined as change in position in a given direction, measured in meters. So that would be your you got the mark just for this change in position in a direction. Give yourself a +1 if you said it was a vector. Give yourself a +1 for that if you said it was measured in meters. So there's a chance to really earn 3 out of 1 marks the way that we do these definitions. Likewise for acceleration, can anybody get all 3 marks brave enough to just state what they've got down? Either you wrote it down or you've anticipated a test correction that you're going to make and you say, I want to get those 2 marks here. Give me a chance real quick. Okay. So clean it up. So based on what we did here, what could you add to what you may have already written down, or did anybody get it? What would we say for acceleration to get all 3 out of 1? I think, hold on, I think they have it in the chat here. Let's give our e-learning colleagues a fair chance. Vector, rate of change in velocity. So that would be 2, okay, to say acceleration is a vector quantity defined as the rate of change of velocity. And now we want to say it's measured in meters per second squared. Very good. So that, having all 3 of those, saying it's a vector is a +1, giving the units is a +1, rate of change of velocity is all you need to put down to get that 1 mark. But you might as well get the +2. So we're already 6 out of 2. You're a great grade on this. But it maybe got a little bit tougher. A man wearing a wingsuit glides through the air with a constant velocity of 47 meters per second at an angle of 24 degrees to the horizontal. The path of the man is shown in figure 2.1. That looks like fun. That's 100 miles an hour also. The total mass of the man and the wingsuit is 85 kilograms. The man takes a time of 2.8 minutes to glide from point A to point B. With reference to the motion of the man, state and explain whether he is in equilibrium. Anybody feel like they got these 2 marks here, and anybody confident in this answer? State and explain whether he is in equilibrium. So the key language is this, constant velocity. All right, so you have to really hone in on that. If you're not appreciating that constant velocity means no acceleration means acceleration is 0. That means F equals ma. Well, if A is 0, that means there's no net force, right? Using Newton's second law. No net force is one of the conditions for equilibrium. The other one is no net torque or moment. And there is no moment in this problem, right? There's no force being exerted on a pivot, to the man. So we would want to say the man is in equilibrium because there is no net force acting and you could, it's because there's no net force acting, because, so you could have said the man is in equilibrium because he's moving at constant velocity, his acceleration is 0, an acceleration of 0, indicates no net force. So you could, word it either way. The man is in equilibrium because there's no net force acting. And just to sort of, reinforce that, he is traveling at constant velocity. So 0 acceleration. Therefore, net force equals 0, as per F equals ma. There, that's a very thorough answer now. I kind of said it twice. There's no net force acting. He's traveling at constant velocity, so 0 acceleration. Therefore, the net force is 0, as per F equals ma. So something like that in your own words, okay? So to state it, to say yes, he is in equilibrium. So if you got that part of it right, that's 1. But if you couldn't say why, you only give yourself 1 out of 2. But if you could state, state something about how you honed in on constant velocity means no acceleration, means no net force, give yourself 2 marks there. Show that the difference in height, h, between A and B is 3,200 meters. So we're given this angle, and we're given enough data to calculate what the hypotenuse is. A person that travels 47 meters per second for 2.8 minutes, okay, is going to go how far? So that's sort of the path to the solution here. You have to calculate the hypotenuse first, and then you've got a nice little triangle there that you can just do a little bit of trigonometry with. So this glide path is going to be a displacement, like we defined up here. Change in position in a certain direction. That's the direction, 24 degrees above horizontal. So the displacement is going to be equal to the velocity times the time, right? If velocity is displacement divided by time, the rate of change of displacement, then displacement is just the product of velocity and time. The velocity is 47 meters per second. The time is 2.8 times 60, right? Because it's 2.8 minutes, but there's 60 seconds per minute. So we really need to convert this into seconds, okay? So you could make, minutes per second times 60 seconds. I'm sorry, 2.8 minutes times 60 seconds per minute, so the minutes cancels. So it's just really the product of 47, 60, and 2.8. That gives you the hypotenuse, 47 times 2.8 minutes times 60 seconds per minute means the glide path is equal to 7,896 meters. I don't know if there's another way to solve it without sort of getting that step. And so this is only 1 mark, but they'd be like, well, there's a half a mark for that. Now we need to say, if we've got h over here, we got a hypotenuse that is 7,896 meters and an angle 24 degrees above horizontal, then the sine function is going to be the one that's helpful in solving this, right? Because it's opposite this angle, and we know the hypotenuse. So the sine of 24 degrees is equal to the height over 7,896 meters. So the height is equal to 7,896 meters times the sine of 24 degrees. Which, if I do that with mental math in my head, I get 3,211 I think it's 0.592534, but I'm just going to round it to 0.6 now because I'm just doing it, like with mental math in my head. And it's even better to say, well, that's about 3,200, right? So it checks out. We've shown that it is 3,200 meters. 1 mark for that. Okay, to kind of set it up like this, you have to have this number as a part of it, and then just, show it with the trig there. Question 3 here says, for the movement of the man from A to B, determine the decrease in gravitational potential energy. So here's where we finally get to hey, some energy stuff that we were studying this week. The decrease in gravitational potential energy is going to be the change in really his height. The mass stays constant, G stays constant. So it's really the change in the height that yields sort of the decrease in potential energy. You can think about it that there's a certain amount of potential energy up here, and the person has decreased their height by 3,200 meters. And that sort of accounts for the decrease in gravitational potential energy, right? Doesn't matter the path that the guy, follows. All that matters for potential energy due to gravity is, again, the component of, sort of that the force is acting in this direction, sort of bring him down. And so all that matters is the vertical component for potential energy due to gravity. So the decrease is just going to be the 85 kilogram mass times 9.81 newtons per kilogram here on Earth, times a height of 3,211.6 meters. So I like to keep the more precise values in my calculation while I'm calculating, and then I round my answer when I'm ready to report it. I think the mark scheme will allow you to calculate this with 3,200, because it's kind of like, let's say you got stumped on this one. You were never able to show that the change in height was 3,200, but you know that that's the change in height because they tell you. Well, then you would just use that value here, right? You'd use the 30. In other words, you can get, you can kind of see your mistake, and let's say they didn't give you the answer, you can get an error carried forward. So if you calculated something else besides this, if they didn't say show, but they just said calculate the height. Well, you calculated a height, but you didn't get it right, but you used the height sort of in this calculation. They would say, oh, well, we've already penalized them for their mistake. They missed the height, but we're not going to keep penalizing them for it. And, question 2, 3, 4, all this sort of continued calculations. So you get an ECF, an error carried forward. But if they give you the value, there's no sort of excuse for an error carried forward. You just use the value that was given. So it's up to you. You calculate with 3,200, or, I still have this value in my calculator. I mean, I did it with mental math. I typed it back in my calculator to do this calculation because, I don't want to do mental math with this. I could, I just don't want to. So then I get this. 2677986. That's also the PIN number to my bank account. Oh, I shouldn't have said that. Just forget that, YouTube. All right. And then that's going to be joules there. And I think we could probably round that to 2.7 times 10 to the 1, 2, 3, 4, 5, 6. 2.7 times 10 to the 6 joules. Megajoules, right? 10 to the 6 is mega. Calculate for the movement of the man from A to B, determine the magnitude of the force on the man due to air resistance. Now, these 2 marks here, I think, are probably maybe the last 2. These last 4 marks are the trickiest ones on the paper, no doubt about it. This one is especially difficult because it's like, well, why did we just calculate this? And so let's kind of use this as an opportunity to put some ideas together now, to really use this as a problem study to appreciate the physics. If you're falling in a gravity field, you might expect that you would be picking up speed, right? Like you're falling down, Earth is accelerating you. That's what acceleration is. It's the rate of change of velocity. So if I'm decreasing potential energy, if a book falls off of the TV over there, it picks up speed, right? But this man is in equilibrium. He's not picking up speed. He's not accelerating. And so we would say what should have been, if there was no air resistance, then this person would have been converting this potential energy into kinetic energy of motion and would have been accelerating, would have been picking up speed, changing their velocity. Because they did not pick up any speed, because they remained in equilibrium, it's sort of like then air resistance must have been doing work on the man. Think about it like that the air resistance did work on the man to prevent that acceleration, okay? So what we really need to do is realize that energy and work are the same thing, that this is the decrease in potential energy, but it didn't show up as kinetic energy, okay? So we can say that this must be equal to the work that was done on the man by air resistance. And so work is equal to force times displacement. This decrease in potential energy is the work done by air resistance, okay? Because there's no increase in speed, all right? Because he stays in equilibrium. He just keeps going 47 meters per second the whole time. So instead of picking up speed, again, so picture this. Instead of picking up speed going down, you might think, oh, I'm going down, right? So I should be going faster and faster and faster. But why do I stay at 47 meters per second? because there's wind resistance acting this way, a resistive force, right? That's just keeping you at this speed. So you're crashing into so much air going this fast that the air is sort of exerting a force in the opposite direction, so preventing you from accelerating. So we're solving for this force. So air, all the air that's sort of between points A and B is doing work on the man, exerting a force in this direction, okay? And we want to solve for that force. What's the magnitude of the force on the man due to air resistance? So this value here is the work. And again, I'm going to calculate with 2, 6, 7, 7, 9, 8, 6. Joules equals the force. I'm just going to divide each side by the displacement. So the displacement, you may recall, was 7896. So that value is what we need. In other words, that is the entire displacement the man underwent. So all along this path, that's where the friction was acting. The friction, due to sort of wind, air resistance. Remember, we said that friction is a non-conservative force. So like the path matters. Gravity is a conservative force. And so all that mattered here was sort of the change in height, right? It didn't matter that he took this whole way to get there. The decrease in potential energy is only based upon this vector here. But for this calculation, we need to divide by 7896 meters. So a joule per meter is a Newton. And so I have that number still in my calculator. I'm just going to divide by 7896, and I get 339, which is about 340. Okay, 340 newtons. I would be very impressed if anybody got that correct. Did anybody get that? That's a tough one. Don't feel bad. It's like, this is really tough calculation. If the explanation made sense to you, if you're like, oh, okay, that's not so bad, once you sort of have, it's that concept, right, that you need to say energy and work are the same thing. And to keep in mind conservation of energy. We should be picking up speed, right? If we're falling in a gravity field, well, why not? Because it's more complicated than that, right? There are outside forces, right? They're acting upon, and in this case, wind. And then the essential question today was to give you a handle on this, but maybe what we'll do is we'll say, like, let's just make this out of 9, and then these will be 2 more bonus points. You already got a chance for some bonus points with the definitions right off the bat, right? Think about this as like, if you do your job as a student, this is really low-hanging fruit to just define things. Like you either know it or you don't. If you've made flashcards, if you've studied your journal, if you've been practicing these, those marks are easy to get. You're just, oh, displacement, I know all my definitions. And moreover, if you know the definitions, you can probably build upon them to do the calculations. Like you can calculate what the acceleration is if you know that it's the rate of change of velocity. Like rate of change of velocity means this, right? And so that really is a way to calculate, if you sort of connect these words with like this equation. So it does build up. These ones are tougher, right? So, and sometimes students find it the opposite. They say, no, the calculations are easy for me. It's memorizing the definitions that are tough, so it depends on what kind of learner you are. It says the pressure of the air, of the still air in A is 63 kilopascals, and at B is 92 kilopascals. Assume the density of the air is constant between A and B. Determine the density of the air between A and B. So here is where we've derived this equation. We did it once in our life, and now we're good to go. We can use it from now on. It gives us sort of a pressure differential. Okay, the pressure of the still air here and here. So we have sort of the change in pressure. We have the heights. We're assuming that the density is the same, and we know that G is 9.81. How should we go about this calculation? Could we just, because we don't really know what the height is, all we know is that the change in height is equal to 3212, let's say, 3211.6. So they don't actually have a value there. So it's kind of like we've got this slice of atmosphere where we know the pressure up here at A is 63 kilopascals. And he goes this path, but all that really matters is that down here, there's higher pressure, right? Because there's more air above your head when you're 12 meters lower. So after this change in height, the pressure the pressure increases to 92 kilopascals. All right. And we want to know the density sort of the air sort of within this little slice of the atmosphere that the man sort of glides through. So if we've got the change in height, we got the change in pressure, and these are, so we would just kind of say 92 kilopascals minus 63 kilopascals. Kilo is 10 to the 3. That would be our pressure. Change in pressure equal to rho, but then G is 9.81 newtons per kilogram, and dividing each side by the change in height, 3212 meters. So a Pascal is a Newton per meter squared. So you get newtons per meter squared up here. That'll cancel this Newton. So you just have meters squared. Newton per meter squared. Well, we'll figure out the units that we're going to get are going to be these kilograms per cubic meter. We can take a minute to prove it to ourselves here. When we're done. Let's crunch the numbers first. So I got 92,000 minus 63,000. It's 29,000 divided by 9.81 divided by 3,212. So I get a density of 0.92, okay, when you actually do that computation. Now let's check the units. So this was, I'll just do the units separate. In other words, I want to make sure I have these units. So a Pascal is a Newton per meter squared. So in the numerator, that's the units I've got. Subtracting units, they just stay the same. You have to have the same units in order to subtract. So in the numerator, I have this, and then in the denominator, I had a Newton per kilogram, right? So the kilogram goes back up here, and then I had a meter down here. So like these newtons cancel, and I have kilograms per meter cubed, which is exactly what I want. So the units work out. All right. Let's call these two marks here. If you got this down as a correction, okay, because I don't know, was anybody able to get this just based on what we did on the chalkboard today? Did anybody kind of just throw those numbers in there and get that? If so, really good job, but just everybody give yourself a +2 on that just for sort of writing it down now. That's not really fair to say, oh, here's, let's derive this equation and go ahead and take a quiz on it. So it's really just something that we've talked about before, where ACE physics, they love to combine different ideas. And so this is something that we'll study in a few weeks. When we do matter and materials, we'll study pressure and density. And you can see that both pressure and density are needed to derive this equation for the pressure of a fluid. So this is the equation for the pressure of a fluid. And we derived it earlier today. So those are freebies, but go ahead and tally up your marks now. So 2 marks for this one. So like a mark for the equation, a mark for the answer, 2 marks for this one, equation, answer. You could have had up to 6 marks for the first 2 definitions, but it's only out of 2. So this is out of 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're not going to count these as part of the quiz. So we're going to say that this quiz is out of 10. If you put your name on your paper, give yourself a mark. If you didn't, just put it on there real quick, okay? Don't deduct the point, just put your name on your paper, okay? Because I like 10, it's more round. Let's make it out of 10, okay? So a mark for your name, okay? You could have earned, if you got everything right, you could have got 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. You could have earned a 16 out of 10 on this week's quiz. I don't think anybody did because I don't think anybody got this one, and I don't think anybody got this one either. But these were freebies anyway, so like you're going to add those two in. If you didn't include the bonus credit for these, don't give yourself full marks, okay, for a correction. Think about partial credit for corrections, okay? So if you just got yourself the 1 mark, hey, that's 100% of the points, right? Because you just said change in position and direction. Or if you only said a vector, that's defined as change in position. You only got 2 out of 1. But if you then wrote down measured in meters, because you're like, oh, it's important that I remember that, I'm going to start defining everything with, you know, whether it's vector scalar, good definition, what are the SI units. Give yourself maybe half a mark for the correction there. You know what I mean? Like you wrote it down afterwards. Don't give yourself full credit because that's not, you know, sort of keeping yourself honest, but, you know, give yourself half credit for making a good correction there. See what I mean? So tally up your marks out of 10, okay, for this quiz. We dismiss in about 8 minutes. If you could send me all of your work this week in the next 8 minutes, then you won't have to worry about it, you know, over the weekend. Please send me a self-evaluation out of 100 points for, you know, what you feel like you earned this week. We didn't have a lab day this week because of the SATs, so all that we're really looking for is the notes that you got, the practice problems, you know, the essential questions for the days that we did meet this week. And then in the email, please tell me again, self-evaluation out of 100 points with your scanned journal pages, and then tell me how many marks out of these 10 for your quiz. Make it very clear, like I got 12 out of 10 or 9 out of 10 or whatever it is. Okay.